asked, we'll have here, and the last class we have started with addressing modes, right? So we'll have a quick recap on those topics, and then we go with problems related to addressing modes, ALU, and data path, right? What is addressing mode? Various methods by which we can access the operands, right? We call this as the addressing modes, right? So first, in general, opcode is the first field, then followed by the operand fields. So the operands can be either it can be in register, in memory, or it can be IO ports. So the uh, different categories of addressing modes are immediate, register, and memory addressing mode. In memory addressing mode, we have different subcategories, right? Immediate means data will be part of the instruction. Register means we will be transferring the data between registers. Memory means we can either access or transmit data from memory to the registers or the IO ports, or from IO ports to the memory, or from the registers to the memory. It can be in either of the bit. So in 8086 microprocessor, we have 12 types of addressing modes, which are listed below. Right, the first one is the implied, next is register, next is immediate, then direct addressing mode, register indirect addressing mode, indexed addressing mode, register relative addressing mode, based indexed addressing mode, relative based index addressing mode, then string addressing mode, IO port addressing mode. In IO ports, we have it can be done either in direct method or indirect method, right? Next is the last one is program memory addressing mode, right? So here we can do it either directly or indirectly, or by using relative program memory addressing modes. So also we have inter-segment and intra-segment addressing modes. Inter-segment means we can jump or move from one segment to the other segment. We know here we have four segment registers: extra segment, stack segment, code segment, and data segment. Right, so each segments are of 64 kilobits bytes. Right, we can move from one segment to other segment. If that is the case, now we say it as inter-segment jumps or inter-segment addressing modes. So if we are moving within the segment, within 64 KB, if you are moving that, then we call that as intra-segment addressing modes. Alright, so here we'll see examples for each and every case. So here it is given. Immediate means data is part of the instruction. So data is provided in the instruction itself, then we call it as the immediate addressing mode. So move BL comma 26. That means 26 is the data which has to be moved to the register BL. So here, if the value is given without brackets, and that is considered as data. If it is given with brackets, now we consider it as address, right? Make a note of it. If it is within brackets, now we say that as address. If it is without that, we say it as data, right? So move BL is 8-bit register, so we are moving 8-bit data 26H to BL register. Move CX comma 4567. So here CX is 16-bit register, so we are moving 16-bit data to the CX register. Right, so this is an example for immediate addressing mode. So next is implicit or implied addressing mode. That means there is no operand present in this. So without operand, if there is zero operand present, we say it as implied addressing mode. Right, set the carry flag, STC, otherwise CTC, clear the carry flag, is an example for implied addressing mode. Next is direct. Direct means address will be given in the instruction. So the data which is given in the brackets is considered as address. So with the help of this address, we are supposed to calculate the physical address. So here what is given is effective address. We call this as effective address. So consider this effective address. Right, add this effective address with data segment value into 10, or any segment register segment address into 10 gives you the physical address. The content in that address is moved to the CL register. That is what it implies. Move CL comma within brackets 9823H. So this implies that the data which is which is here, which is given. The data which is given here is considered as address. With the help of this address, we can calculate the physical address. The content in that physical address is moved to the CL register. Alright, so next is register addressing mode. So here in register addressing mode, move bx comma cx. So that means cx content is moved to bx register, bl content is moved to cl register. Bx and cx are 16-bit registers, so we'll be moving 16-bit data from cx to bx. Bl and cl are 8-bit registers, so we'll be moving 8-bit data from BL register to the CL register. Right. So next is register indirect addressing mode. That means here indirect way of accessing. The address will not be given in the instruction. Instead, the effective address will be stored in a register. Alright, the effective address will be stored in a register. With the help of that effective address, we are supposed to calculate the physical address. So here the example is move within brackets di, comma bx. So here this indirect register can be either DI or SI or BX or BP. Any one among this can be used as the indirect register to store the address value. So here it is DI register. So in DI we will be having an effective address. Right? With the help of that effective address, obtain the physical address. Right? So here we are going to consider data segment value as 7205. Right, so this is the data segment value. So to obtain the physical address, the formula is data segment address into 10 plus effective address. So the effective address is taken as DA register content. So DA register content is taken as 30, right? So 7205 into 10 gives you 72050 plus the effective address 30 gives you 72080. So this is the physical address which we have obtained here. So if this is the case, BX is 16-bit register, right? So the content in the BL register is moved to 72080 location, and the content in the BH register is moved to 72081 location, right? So here this 16-bit value is moved to 80 location and then 81 location, right? 88 bits, in that way it has been moved. So this is an example for register indirect addressing mode. Right, so here if we consider only the segment index register, we call it as the indexed addressing mode. If it is bx or bp alone, now we say it as based addressing mode. If we consider both the index, which is index register as well as base registers, now we say it as base plus index addressing mode. So it is given in the coming slides. So based indexed addressing mode, so example is move ax comma within brackets bx and then within brackets si. That means this is an example for base indexed, otherwise base plus index addressing mode. Alright. So here combination of bx and si, if we add together, we will be obtaining the effective address. This is what given here. The effective address is bx plus si. It is bx plus si. It is given here. Alright. So here, if we add these two, we will be getting 2530H. So this is the obtained effective address. Right? Add this with the segment address into 10. So you will be obtaining 42530H. So this is what the physical address which we have obtained. The content in this location is moved to AX register AL, and the content in 31 address location is moved to AH register. So this is what will happen for this case. Next is register relative addressing mode. So in register relative addressing mode, some relative address will be given. So that is BX register or BP or SI or DI. Consider any one of the register. Along with it, add an 8-bit or 16-bit displacement value to obtain the effective address. That's what given here. Effective address is bx plus some displacement value. So that you will be obtaining 1050 as the effective address, right? So with this effective address, add the segment address into 10 value and obtain the physical addresses 41050 H, right? So the content in this location is moved to AL and the content in the next location 51 is moved to AH register. So this is what will happen for register relative addressing mode. Next is relative based indexed addressing mode. So here relative, that is displacement value, will be added with base value as well as index value. So all three together. So this is the example here. Xi bx value as well as displacement value. So move ax comma 5000, then bx si. So displacement value is given as 5000. So si value is taken as 1000 and bx value is taken as 2000. So it can be either bx or bp, si or di. We can consider any one register, right? And then add all these three together to obtain the effective address. So add the obtained effective address with the segment address into 10 value and then obtain the physical address location 48000H. So this is the physical address which we have obtained. So here the content in this location is moved to AL register and then the content in the next coming register is moved to the AH register. So this is what an example for register relative based indexed addressing mode. So next is program memory addressing mode. So it can be direct program memory or relative program memory or indirect program memory. Direct means directly address will be given. Jump to the location specified. So jump to the location 2000. Relative means from the current location, just move 2 steps forward. Jump 02 means it is an example for intra-segment jump. This is an example for inter-segment jump. The next is jump bx register. That means bx is given in the brackets, right? That means this is an indirect method of accessing. So indirect program memory addressing mode. This can be either intra-segment or inter-segment depending upon the address what we are going to give here. Right? If the address we are going to give here is within the segment register, then we call it as intra-segment. If it is going to move to the other segment, we call it as the inter-segment jump. Right? But this is an example for indirect way. So since address is given in the BX register, we say it as indirect program memory addressing mode. So next is an example given here. Consider a processor with, this is previously asked the gate question. Okay. So consider a processor with 64 registers and an instruction set of size 12. Right. So here we are going to consider 64 registers. So please note it down, 64 registers. Then how many address lines are required to access the 64 registers? Anyone please try it out. If it is 64, to access 64 registers, how many address locations are required or address bits are required? We know now 2 power 5 is 32. So 2 power 6 is 64. So 6 bit value, 6 bit or 6 address lines are required. So make a note of this. So depending upon the question given, we can calculate the number of address lines required. Right? So and an instruction set of size 12. Each instruction has 5 distinct fields, namely opcode, 2 source identifiers, 1 destination register identifier, and 12-bit immediate value. Each instruction must be stored in memory in a byte aligned fashion. So this is what given here. Right? If a program has 100 instructions, the amount of memory in bytes consumed by the program text is. So this is what asked here. Alright. So it is given that each instruction has 5 distinct fields. Right? So namely opcode. So we know in general opcode requires 4-bit. Then 2 source register identifiers. So we from the 64 registers we can come to a conclusion that each register occupies 6 bits. So 2 source register plus 1 destination register. So that is what given here, 4 bits plus 3 6 bits, right? And then followed by 12-bit immediate value. So we are having a 12-bit immediate value, right? So if you add all these together, you will be obtaining 34 bits. So every instruction will occupy 34 bits. Each instruction will occupy 34 bits. What is given? For 100 such instructions, what is the memory required? It has been asked. So one instruction size is 34 bits. Otherwise, I can say it is 5 bytes. 34 bits. Now, to store this 34 bits, we require 5 bytes or 5 locations. Right? 5 bytes is required to store this 34 bits. Then the 5 bytes into 100 instructions will give you 500 bytes. So I can say 500 locations or 500 bytes is required. In this way, we are supposed to find. So depending upon what is given. So here they didn't give directly. So what is the number of bits required to store the register value? But here it is indirectly given in the question. 64 registers. So to access this register, we require 6 bits. That means each and every register will occupy 6 bits. So we are supposed to find in that way. So next is a program. This is the same program which we have seen in the last class, but the parameters which is asked and considered here is slightly different. So consider the following program segment. Here R1, R2 and R3 are the general purpose registers. Right? The size of the instructions are given the right side. So the instructions and the operations is performed as given here. Right? Move R1, 3000. That means the content in the 3000 location is moved to R1 register. So here in 3000 it is given as 10. So 10 is the value which is moved to 10 is the value which is moved to R1. Alright, and then move R2, R3. That means R3 is given in the brackets. The content in the register R3 is moved to R2 register. Right, in R3 it is given as 2000. Right, in 2000 the value given is 100. Right, in 2000 the value given is 100. Right, this is the value which is moved to R2 register. Now R2 register will be having 100. Then add R2, R1. That means R R2, R1. In R1 we are having 10 and in R2 we are having 100. So 100 plus 10 is added and it is stored in the register R2. Right. Next is move the content from R2 to R3, then increment R3. So here in this program, in the last class we have seen when an interrupt occurs at this instant in the increment R3. So if the interrupt occurs now, what will be the next address? So that in that way the question is asked. But now the same program is given, but what is asked is, right, it is given that from 2000 to 2010 location we are having 100 as the data. The program is loaded from the memory location 1000. Alright, all the numbers are in decimals. Assume that the memory is word addressable. Right, for each and every instruction, the word number of words required is given. After the execution of the program, the content of the memory location 2010 is asked. 2010 what it will contain, that is asked. Right? In 2010 we'll be having the value. What is so here next step is increment R3 and then decrement R1. So now the loop count is decremented by 1. Right? 10 becomes 9. Check whether it is 0 or not. If it is not 0, repeat the process. So go to this loop. Repeat the process. This is what given here. That is what explained here. The loop runs 10 times, starting from memory location 2000. Initially 10 plus 100 gives you 110. Next, in the next iteration, the value of R1 becomes 9. So 2000, so 100 plus 9 gives you 109. So this process will be repeated till the R1 value becomes 0. So once it becomes 0, it will come out from the loop. So now at the memory location 2010, what's the value? It is 100. So here this loop instructions doesn't affect the value in the location 2010. So simply I can say in 2010 I'm having 100. So here that's what given 100. It is option A. So option A is 100. So this is the result. This is the answer, right? The next is uh, right. Consider the next one. Consider the following code sequence having the five instructions I1 to I5. Five instructions are given, right? Each of these instructions have the following format. First one is the opcode followed by RI, RJ, and RK, where operation OP is performed on the content of registers RJ and RK, and the result is stored in the register RI. So RI is the destination register, RJ and RK are the source registers. So keep this in mind. RI is destination. Right? Five instructions are add R1, R2, and R3. Mul R7, R1, R3. That means in addition, R2, R3 content are added and result is stored in R1. In multiplication, R1, R3 values are multiplied and result is stored in R7. Sub R4, R1, R5. That means R1 and R5 values are subtracted and result is stored in the register R4. Add R3, R2, R4. So here R4, R3 values are added and result is stored in the register R3. See here we are just storing the value R3, but here R3 is given here. Check it out, right? Mul R7, R8, R9. So R8 and R9 values are added, multiplied, and result is stored in R7. So consider the following three statements. So what is given is there is an there is an anti-dependence between instructions I1 and I5. There is an anti-dependence between instruction I2 and I4. Within an instruction pipeline, an anti-dependence always creates one or more stalls. Which one of the above statement is or correct? So we are supposed to find which is correct, right? First, before finding the answer, we have to know what is anti-dependences. What is anti-dependence? Does anyone know? What is anti-dependence? That means we'll be calling a value before it is performed. So that's what anti-dependence is also known as write after read. Occurs when an instruction requires a value that is later updated. That means the result will be coming afterwards, but we'll be calling that value before itself. So if that is the case, we say it as anti-dependence. So now you can check it out here in the program where anti-dependence comes. So here R2 and R3 are added and result is stored in R1. Again R1 and R3s are multiplied and result is stored in R7. That means these are the source registers, right? R1 and R5 is source. R1 is occurred here, right? R1 occurs here, so that is the destination value. So that is called again here. It is called again here, and the result is stored in R4. But check it out here. R3 is given in the destination, but R3 is given here in the source. But this occurs before that one. Here, R1 is the resultant value and R1 is the source. It comes after that, so no problem. But here, R3 is coming before here and here. R3 is coming before itself. Alright? But we are getting the value here only. We are obtaining the R3 value here only. So it is combination of R2 and R4. Addition of R2 and R4 gives you R3. So we are calling that value before it occurs. Right? So this we call it as anti-dependence. So this occurs between what are the instructions which occurs here? It occurs between the instruction either I1, I4 or I2, I4. So in the question it is given the here as I2, I4 or I2, I5. I5 will not bother because R7 is destination. Here also R7 is destination. Alright, it doesn't happen here. Anti-dependence doesn't happen between I2 and I5. It occurs between I2 and I4 only. So I can say only S2 is true. So the answer is D. Only S2 is true. That's what given here. Antidependence. If for the first case there is no antidependence, for the second case antidependence is there. Next one there is no antidependence. So how can we rectify this antidependence? It can be removed by renaming the variables. So instead of R3, if I give some other value, then antidependence will not occur. This is the way we can remove antidependence. Next is simple mission cycle values. Find the mission cycle value for the crystal frequency given. Right, this we have seen. In this model, we have seen a program in the last class for 8085 microprocessor. Alright, so from the crystal frequency, we can obtain what is time. Alright, mission cycle is number of cycles per frequency. Number of cycles per frequency. Alright, the time is 1 by f. So we can obtain the time. Right, now mission cycle is, we say it as 1/12 of the crystal frequency. So 12 into the time, that gives you 1.085 microseconds. If the crystal frequency is 11.0592 megahertz. So always make a note here. One mission cycle period is 1/12 of the, sorry, operating frequency, right? Operating frequency is 1/12 of the crystal frequency. Please make a note of this. Operating frequency is 1/12 of the crystal frequency, so you can obtain the operating frequency. From the operating frequency, you can obtain the mission cycle period. Mission cycle period is 1 by operating frequency. Right? Operating frequency is 1/12 of the mission cycle period. So what is the value? It is given 1/12 of the crystal frequency. So crystal frequency is 7.0592 by, well, you can obtain the frequency value and then find the time. So time is 1 by f. So by that you can obtain one mission cycle period. It is 1.085 microseconds. The similar way, some program will be given and you will be asked to find the time delay for that program. Each and every program, what is the number of mission cycles obtained will be given. For example, if it is no operation, it requires one mission cycle. Then the same for to execute that instruction, if we require the same 1.05 microseconds. If addition instruction or if written instruction is given, that requires two mission cycles. So I can say 1.085 into 2. That will be the time taken to execute the written instruction. So in that way, some instruction sets and its corresponding mission cycle period will be given, and you will be asked to calculate the time delay. In that way, you can it will be given. All right. So next is interrupts. So interrupts are used to handle a variety of problems. This we know, no? So what happens when the interrupt is given? The current execution stops. In general, we say the current execution stops, but please make a note. The current execution stops will be saying that means the current instruction which is executing will be executed. Before going on to the next instruction, the execution stops, right? And then the code segment and IP address will be moved to the stack, right? Once after the interrupt is given, the ISR subroutine address is found and with the control is transferred to the subprogram. After executing the subprogram, there will be a last instruction will be return interrupt return instruction. So after seeing that, the control again comes back to the main program and it starts executing the program from the next line where it left. Right? So from the main program, the control is transferred to the subroutine or service program. Transfer of control addressing modes. It can be either PC relative addressing mode or base register addressing modes. And types of interrupts, we have maskable and non-maskable interrupts. NMI, non-maskable interrupt. NMI is an example for non-maskable. In maskable, we have hardware as well as software interrupts. INTR is an example for hardware maskable interrupt. Then int 0 to int 255. So 256 interrupts we are having as software interrupts. So int 0 to int 55. So these are the examples for maskable software interrupts. Non-maskable means that interrupt cannot be enabled or disabled. On the basis of devices, we can have external interrupt, internal interrupt, or software interrupt. External interrupt, the name itself says it can be either from the input or output devices. Internal not due to some error conditions which occur in the internally, or yes, we can say in that way. So that is internal interrupt. Software interrupt is by using the software instructions we can give the interrupts. So here the number of basic cells in a 16 cross 4 number of cells, it has been asked number of cells. So 16 cross 4 RAM. So 16, it consists of 16 words of 4 bits each. So I can say 16 words of 4 bit each. That is the case. 16 into 4 gives you 64. So it has total 64 binary cells. So next is ALU data path. In general, CPU is divided into two sections. One is data section, other one is control section. Data section also it is also called as data path. Right. So here the registers ALU and interconnecting bus are collectively referred to as data path. Control section is basically the control unit what we have. So bus, the collection of wires we say it as bus. Data bus means number of lines which are required to transmit data between registers or between memory and the register in that way, whatever it is. Data is transmitted through the data lines. So that we call it as data bus. Address for accessing the memory. Number of lines required that is clubbed together and it is called as address bus. Alright, control buses to send the control signals. We'll be having a bunch of wires. We call that as the control bus. So we know no, these are the basic terms. Program counter, it holds the address of X instruction to be executed. Instruction register holds the executing instructions IP address value. Then instruction catch, register file, arithmetic and logic unit, data catch, multiplexer. The ALU will perform all the arithmetic and logical operations. So right, so these are the terms which we'll be using: single cycle data path, multi-cycle. Each instruction takes multiple clock cycles. If it takes only one clock cycle, we say it as single cycle data path. In single cycle, all the cycles should be of equal length. In multi-cycle, cycle time is 2 nanoseconds. Next is arithmetic and logical unit. And the figure is given. Special register, one of the input ALU. Output of ALU stored back in the accumulator. Alright, what are the operations performed in the ALU? The resultant will be stored in the accumulator. This is an example with multiple registers. Instruction path, program counter keeps track of the program execution. Instruction registers will have the current instruction value address in it in relation to data path. Program counter may be incremented through ALU. Amount of the question it is asked in the previous question paper is The amount of ROM needed to implement a 4-bit multiplier is. So to have a 4-bit multiplier, what is the size of the RAM which is required? The size of the RAM which is required here is 2 kilobits. 4-bit multiplier means you can check it out. 4-bit combination, the maximum value what it will be. 4-bit 2 power 4-bit multiplier. 2 power 4 is 16. Alright. So I can say we require 2 kilobits. The CPU generally handles an interrupt by executing an interrupt service routine. This is the statement given, and the options given are: as soon as an interrupt is raised, by checking the interrupt register at the end of the fixed cycle, by checking the interrupt register after finishing the execution of the current instruction, by checking the interrupt register at fixed time intervals. So what is right here? You can just find it out. A CPU generally handles an interrupt by executing an interrupt service routine. So if the interrupt is given, it will execute interrupt service routine, okay. But when it will go and check whether the interrupt is given or not. So after execution of each and every instruction, it will check for the interrupts. So by checking the interrupt register after finishing the execution of the current instruction, after execution of current instruction, CPU will check whether the interrupt is given or not. Right. So the correct option is answer C. Which of the following is are true of the auto increment addressing mode? It is useful in creating self-relocating code. Otherwise, if it is included in an instruction set architecture, then an additional ALU is required for effective address calculation. The amount of increment depends on the size of the data item accessed. So which is right here is 3. That is option C. 3 only. The amount of increment depends on the size of the data item accessed. Use of multiple register windows with overlap causes a reduction in the number of memory access. For function locals and parameters or registers, saves and restores, instruction fetches. So when we go for multiple register windows, it causes reduction in the number of memory access for register, saves and restores alone, not for the other cases, right? We will see few cases here with others and then we'll come back with this. Alright. So here an example is given. If AL is equal to 35H and BL is 13H, after the execution of the following instructions, add AL comma BL. So add AL comma BL. Right, the AL value is 35 and BL value is 39. BL value is 39. Right, so if you add 35 and 39, you will be obtaining the value as 14, right? That is 35 plus 39. If it is the general addition, now you'll be having 674 you'll be getting. Right? If you adjust for the ASCII code, if you adjust it, triple A is adjust ASCII after addition. Right? ASCII code should start with 35 here. There is 3. Right? If it is the 0, na, it is 30. If it is 9, na, it is 39 in that way. So the answer should be here 4. That is, generally we'll be getting 74 here. So the higher part will be masked and you'll be getting the answer as 04. So the correct option is D. Right, the correct option is D. So this is the right option, D. Right, the correct option is D. This is ASCII adjust after addition. So the triple A stands for ASCII adjust after addition. Alright, okay. So the answer will be 4 directly. 9 plus 5 is 14, no? So that 4 will be getting. The higher order portion will not be getting here. What is the maximum capacity of the memory that can be interfaced to the microprocessor which contains 20 address lines? We now know what's the maximum capacity if it has 20 address lines. The formula is 2 power n, where n is the number of address lines required. Right? So 2 power n, 2 power 20 is value is 1048576. That is equal to 1 MB. So this is the capacity of 8086 microprocessor. For 8086 microprocessor, we have 20 address lines. So about 20 is 1 MB. So 1 MB is the maximum capacity of memory which can be accessed by 8086 microprocessor. So next example, next problem, next question is what are the status of carry and auxiliary flags after performing the subtraction of 0F from F0? So we are going to subtract 0F from F0. Right, be clear with it. We are going to subtract 0F from F0. So F0 minus 0F. What will be the result? This is what the question is. So what are the flags which will be affected for this? So by default, we can no subtract 0F from F0. So F0 minus 0F. Alright, minuend is greater than the suprahend. Minuend is F0, suprahend is 0F. So since minuend is greater than the suprahend, so we can simply say the carry flag will not be set. The options given are both the flags are reset, both the flags are set. Carry flag is set and the auxiliary carry flag is reset. Carry flag is reset and the auxiliary carry flag is set. Right, after performing this, we can come to a conclusion that carry flag is reset because it is larger number minus smaller number. That is, minuend is larger, suprahend is lesser. So there is no need for the carry flag to be set. Right. So next is when we consider the lower part, lower nibble when we consider it is 0 minus f. So there the lower nibble is lesser number minus larger number, smaller number minus larger number. So there is need for the auxiliary carry flag to be set. Right. So we can say auxiliary carry flag is set and the carry flag is reset. So the correct option is D. Carry flag is reset and the auxiliary carry flag is set. So next is if DL is equal to EF in hexadecimal and the carry flag is reset, what will be the content of DL register after execution of the instruction ROL? ROL, what it will do? It will rotate the data which is given left by 1 bit. Alright, rotate left by 1 bit. That's what will happen if ROL instruction is given. So DL value is given and the carry flag is reset. Okay, what will be the content of the EL register? So DL comma 01 is the instruction given. So in the solution you can see ROL, what it will do, it will rotate the DL content by 1 bit left. The content of the DL is EH, right? So it is E means it is 1110 and H na F na it is 4 ones. Alright, so when we rotate it left by 1 bit, what will happen here? Initially the carry flag is reset, right? Rotate left by 1 bit. So MSB part will be moved to the carry. Right. Also MSB part will be moved to the LSB part. So this MSB part 1 will be moved to the LSD part as well as it is moved 1 bit left, right? So then what will happen here? So you'll be getting 1101 followed by 4 ones. So which, then the value is EF becomes DF. So in hexadecimal the value is DF. So the right answer is B. Option B is the right answer. DF is the right answer. So you can obtain in this way. Rotate means just it will rotate. MSB becomes LSB. If it is rotate right now, LSB becomes MSB. So make a note of it. Left now, MSB will be the LSB part. If it is rotate right now, LSB will be the MSB part. Which of the following instruction is equivalent to XOR AL, comma AL? So what will happen if we XOR two data which is of same value? The XOR operation, anyone can say. What is the result for XOR operation? Open your mouth, guys. The two inputs are same. What happens? So make a note of it. For XOR gate, if the inputs are different, output is 1. If the inputs are same, output is 0. Right? We know no. A bar B plus A B bar is equal to Y. This is the equation for XOR gate. Right? So if the inputs are different, output is 0. If the inputs are different, output is 1. The inputs are same, then the output is 0. So here when we do the XOR operation between AL as well as AL register, two AL registers, two values, that is by itself if you do the XOR operation, resultant will be 0, right? So here for which instruction the value will be 0. Check it out. R AL comma 00. That means the AL value remains the same. Whatever the AL value, that will be the same. So when we do AND operation between AL and 00, whatever the AL value is, the answer will be 0. If you do OR operation between AL and FF, whatever the AL value is, the result will be all ones. If I do AND operation between AL and FF, whatever the AL value is, that will be the answer again. But what should I get? I should get 0, right? Since XOR of AL, comma AL, the answer is 0. So answer B is right. So and AL, comma 00 gives me the answer as 00. That's the right answer. So pipelining. So what is the specialty of 8086 microprocessor? What is pipelining? What is specialty of 8086 microprocessor and what is pipelining? Right? When executing an instruction fetching can be done. Right? We call this as pipelining, right? So instead of wasting the time for execution, in the meanwhile, we'll be fetching the other instruction and that will be kept ready to execute once this execution is over. This process we say it as pipelining. So that is there in 8086 microprocessor. Right, so what is the question given here? You can take it out. Register renaming is done in pipeline process. For what register renaming is done? That is to handle certain kinds of hazards or as an alternative to register allocation at compile time. For efficient access to function parameters and local variables as part of address translation. So these options are wrong. So the register renaming is done in pipeline process to handle certain type of hazards. Next topic is data path and the control unit. Then instruction pipelining. So these things we have seen before itself. So after that instruction pipelining, as if I said, it reads instructions from the memory while previous instructions are being executed. That's what I said. While executing the instruction, it will get the next instruction subcode. Right? Instruction fetching is done while executing an instruction. That is what we say it as pipelining. So by this way, we can execute multiple instructions at the same time. So it is to speed up the process. So what is overlapped here? The overlapping of fetch, decode, and execution phases of an instruction cycle is done here. So by this way, throughput of the computer system can be increased. In most of the cases, computer needs to process each instruction in the following sequence of steps. What is the steps to be followed? Fetching the instruction, then decoding, then calculate the effective address, fetch the operand from memory, execute the instruction, store the result. Right? This is what in general happens, no? But we will combine you call this all together as execution phase. Fetch, decode, and execute. Simply we say it that way. In the execution phase, what happens? Effective address is calculated, operands are fetched, then instruction is executed, and the result is stored. So this is what happens in the execution phase. The arithmetic pipeline. This will divide the arithmetic problems into various subproblems for execution in various pipeline segments. It can be used for floating point operations, multiplication, and various other computations. Right? That is what given in the next slide. So pipelining is done to handle certain kinds of hazards. That's what we have seen before. So here, consider this sequence of machine instructions given below. So the program below uses 6 temporary variables. So what are the variables given? A, B, C, D, E, and F. Right? So A is given taken as 1, B is 10, C is 20, and D is A plus B. E is C plus D. F is C plus E. B is C plus E again. C plus E itself has 2 variables F and B. E is B plus F. D is 5 plus E. Return D plus F. Assuming all operations take their operands from registers, what is the minimum number of registers needed to execute this program without spilling? So ABC value is given. With that, we can calculate D register value. Right, also we can calculate C plus D gives you E, and then we are using C as well as E value in F, and then for storing B, C plus E is added and stored in B. So F is same B value, right? Next, E is B plus F value, B plus F value. D is 5 plus E, return D plus F. So to execute this, right, if you consider what is the number of things which is required. Alright, now we can consider here in this type of compiler questions. I guess we can go for mapping in this way, right? What is A, what is B, what is C, you can write, and then with the help of that we can obtain what is D, right? A value is 1, B value is 1. Then with that, if you add these two, you'll be getting D, right? D and C is added, you'll be getting E, and E and C is added, you'll be getting F as well as B. Alright, B and F are the same values. Alright, if you add this F and B, you'll be getting E. In E and 5 is added, you'll be getting D value. When D is added with F or B value, you'll be getting the answer here. So in this case, if you find in this way, so here you'll be getting the answer as 6. Correct answer is B. The minimum number of registers required is B. So it is 3. Minimum number of registers to store the value is 3. So A, B, and C, the value which is stored here is 3 registers. So we are in need of 3 registers to execute this program, right? That's what given here. Which of the following is not true in a pipelined processor? Bypassing can handle all raw hazards. Register renaming can eliminate all register carried WR hazards. Control hazard penalties can be eliminated by dynamic branch of prediction. So here the right options are 1 and 2 only. Right, the option A is right. So it can be this bypassing can handle all raw hazards. So here we cannot solve all the problems by bypassing the raw hazards, right? Register renaming will also will not eliminate all the hazards, right? So the right answer is option A, 1 and 2. Then we'll go with some other cases. We'll see with this problem. Consider a pipelined processor with the following 4 stages. Right, instruction fetch, instruction decode, IF is instruction fetch, ID is instruction decode and operand fetch, EX is execute, WB is write back command. Right? If IF, ID and WB stages take 1 clock cycle each to complete the operation, IF is instruction fetch, ID is instruction decode and operand fetch. WB is write back command, EX is execute. Right? If IF, ID and WB stages take 1 clock cycle each to complete the operation, number of clock cycles for the execution stage depends on the instruction. The add and the sub instructions need 1 clock cycle and the mul instruction needs 3 clock cycles in the execution stage. So for addition and subtraction, that requires 1 clock cycle. A multiplication instruction requires 3 clock cycles in the execution stage. Right? Operand forwarding is used in the pipeline processor. What is the number of clock cycles taken to complete the following sequence of instructions? The number of cycles taken by each instruction is given, right? And we are asked with the number of clock cycles required to complete the following instruction. So add R3, say R2, R1, R0. That means R1 and R0 is added and result is stored in the register R2. Right? Next instruction is multiplication instruction. Alright, so this multiplication instruction requires what is done here is R4, R2, R3, R2. That means R2, R3 values are multiplied and the result is stored in the R4 register. Then subtract R6, R5, R4. So this requires, so here R4 and R5 values are obtained and then subtraction is performed and the result is stored in R6 register. Right? Instruction fetching. For instruction fetching, we need one clock cycle. And then for instruction decoding and operand fetching, we require one clock cycle. For write back, we require one clock cycle. Then execution of this addition and subtraction instruction takes one clock cycle. Multiplication takes 3 clock cycles. Right? This is the case. So here for fetching we require one clock cycle and for executing we require one clock cycle. So 2. Right? So for addition operation we require 2 clock cycles. For subtraction similarly for fetching one clock cycle, for execution one clock cycle. So 2 plus 2 is 4. Right? For multiplication, for fetching we require one clock cycle and for performing this multiplication operation we require 3 clock cycles. Right? 3 plus 1 is 4. So 4 clock cycles for multiplication instruction, 2 clock cycles for addition instruction, and 2 clock cycles for subtraction instruction. So on the whole, 4 plus 2 plus 2 you will be having 8. So 8 is the answer here. Right? So the correct answer is 8, which is required to execute this sequence of steps. Number of clock cycles required is 8 because multiplication for execution of multiplication we require 3 and for fetching we require 1. For addition, for execution we require 1 and for fetching we require 1. For subtraction also for execution we require 1 and for fetching we require 1. So 1 plus 1 is 2 for subtraction, 1 plus 1 is 2 for addition, as well as 1 plus 3 is 4. So 4 plus 2 plus 2 is 8. So on the whole we require 8 clock cycles to execute this instruction. Right? So this is an example. Then what else is given? So one more question is given. Consider a 4-stage pipeline processor. The number of cycles needed by the 4 instructions I1, I2, I3, I4 in stages S1, S2, S3, S4 is shown below. Right, S1, S2, S3, S4 is given, and I1, I2, I3, I4 is given. So number of cycles needed to execute this is given in the table. What is the number of cycles needed to execute the following loop? For I equal to 1 to 2, I1, I2, I3, I4. To execute this instruction, what is the number of cycles required is asked, where I value is 1 to 2. So this sequence of instructions should be executed twice. I1, I2, I3 and I4 should be executed twice. So to execute this, we require 23 clock cycles. So on the whole, if we add this, we'll be getting 23. So the answer is 23. We'll see if the problem before what we have skipped here. One case we have skipped this, right? it will be 4. Right, it's done. I think we are left with 4. Right, in addressing modes, I'll ask in question. Right, is just find what is the type of addressing mode for it is. Right, in that way also the questions will be asked. Right, for example, if I'll be giving you an instruction, you are supposed to find whatever addressing mode it is. Right, move ax comma bx in brackets and then 08 in brackets. What type of addressing mode it is? Anyone can answer. You can try it out. Move ax comma bx in brackets and in brackets will be having 08. What is the type of addressing mode it is? Yes, so it is relative addressing mode. So in relative addressing mode, you'll be having some displacement value which has to be added with either any of the registers. It can be index register or base register, BX or BP, SI or DI. Right? Add the displacement value with it and then obtain the effective address. Right? Add that effective address with the segment address into 10 to obtain the physical address and then the content in that location is moved to AX register. This is an example for this is an example for this is relative addressing mode. So with this we'll be stopping here, students. Okay, we'll start about memory in the next class. Right, with this we'll be stopping here.